on Monday, we discussed the neural network. We defined a definition of some components of the networks, and some of the typical networks, especially for computer vision. We will introduce the neural network architectures for language models when we talk about language models. And today we're going to talk about backpropagation. As we said last time, this is the algorithm to compute the gradient of the loss function with respect to parameters. So maybe just a very, very brief review. So the background you need from last lecture was that, there is a function, let's call it the loss function or the cost function, which is the average of the cost function of individual examples. So each example I has a cost function, and this cost function is something like maybe a loss, maybe cross-entropy loss, for example, on some model output h theta of x, and some label y, and maybe the ith input and the ith label, something like this. So, and when you run SGD, the most simplistic version of SGD is that you update the parameter theta to theta minus some eta times the gradient on some example, maybe it says I sub k theta, where I sub k is sampled randomly from the data set. So something like this. And the key focus of this lecture is that how do we compute the gradient, this object? How do we compute the gradient efficiently with respect to the parameters, right? So we know how to compute this last time. Suppose you have defined the model by combining many of the components. It's a multi-layer MLP, with, machine application, with some activation functions, many layers of that. It's a very complex network. That's what this guy is. And how do you compute the gradient of this function, right? This is just the same as this and same as this one. And how do you compute the gradient with respect to the parameter theta? So that's the whole focus of this lecture, which is kind of like actually this kind of questions, is one of the kind of like the most technical questions you can ask in deep learning these days, because all the other things you cannot really objectively answer in many cases, like how do you tune learning rate, how do you design your data sets, all of those are kind of like subjective in some sense. So that's why I think there was a long time when all of these kind of like research labs, when they interview people, they ask how you do backpropagation. I think that's probably still the case for some of the frontier labs. I don't know exactly. But so this is kind of like a non-trivial algorithm that is really an algorithm that is needed for every training jobs, under the hood, even though that's, you don't really have to do it yourself these days. It's called backpropagation or auto differentiation. It means that it's automatable, right? So you don't really have to do it yourself. But I think it's something that is good to understand, because, some of this kind of like other decisions you make depends on fundamentally how it works to some degree. So that's why we're discussing it. Okay. So I think it's kind of like so we're going to start with a more generic view to think about how do you take gradients in general when you have a kind of like a circuit or kind of a very general function. And we're going to apply that kind of like to neural networks. So basically this kind of like auto differentiation is not specific to neural networks. You can use it for almost every nonlinear functions as long as you can define the nonlinear functions in the forward pass. Like as long as your function can be computable in a specific way, when you compute the function value, then you can compute the gradient. So that's what I'm going to write here in a kind of like in an abstract way. So let's say suppose you define some, let's say, differentiable circuit. So I'm using this as kind of like a, or maybe differentiable networks. So let's say this is kind of like basically a network that is composition of, sequence of arithmetics operations. And maybe other elementary functions. So arithmetic operations means like, for example, plus, minus, division, so on and so forth. And elementary functions could be something like, maybe cosine, sine, maybe exponential, cosine, sine. The exact definitions here don't really matter. I'm just trying to maybe ReLU. This is what I mean by elementary functions. Sigmoid. So basically you can say, I have an input x1, in the circuit kind of world, people drawing these things like this, right? You have input x1, x2, then you have some gate plus, then you do the compute, the sum of them. And then maybe you can have x3, and then you can have a gate, which is kind of like a gate or operation, which is like maybe times, and then you compute. This means that you do x1 plus x2 times x3. And maybe you can reuse x1 times x2 here. Maybe let's say you can do plus, then you just add another. Okay, so then this one is x1 plus x2 plus x4, and then you can probably aggregate again, so on and so forth. So you can see that the difference between this and the formula is that when you have a circuit, you can reuse some parts. But if you have a formula, you have to expand everything. So if x1 plus x2 is used twice, then you have to write x1 plus x2 twice in your formula. But in the circuit science, you don't have to recompute it again. So that's the only minor difference. Anyway, this is just some kind of a computational graph in some sense. The exact details don't matter. The claim here is actually pretty profound, which is so the theorem here, of course, it's an informally stated theorems because, if you really want to make a formula, you have to specify exactly what all of this kind of composition really means. Then you have to go through a lot of jargons, which is not necessary for this lecture. So the theorem is that suppose, let's say a differentiable circuit of size n. And here, what does size mean? Size means that how many kind of operations you have, or how many of these operations you have. So, and size n computes a real value function. So I'm only thinking about a circuit where there's only one output, a scalar output, because that simplifies my life a little bit. So a real value function, let's say this function is f. So this is what the circuit's job, right? It's computing of a function that maps L input to one scalar. Suppose you have such a function which is computable by this differentiable circuit. Then the gradient, let's say, gradient of f with respect to the input. So first of all, maybe let's look at a type signature here. What's the gradient, dimension of the gradient? You have a function that maps R inputs to one input. The gradient is a L-dimensional vector, right? Because for each coordinate, you have one partial gradient. So this is a L-dimensional vector, and this can also be computed. In time, say O of n. So you don't have to spend much more time by a circuit of size O of n. So by the way, when I talk about time and circuit, here I'm implicitly assuming that each of these very basic operation takes O of one time. It takes 1 unit of time. And that's why to compute the function, you just go through this circuit. Because the size is n, it takes O of n time, right? To compute the function. And I'm claiming that if you have such a circuit that computes the function f, then the gradient of this circuit, of this function, can also be computed in similar time. And also the gradient itself is representable by a circuit, which is also an interesting fact. So in some sense, this is saying that, okay, in deep learning, people call computing of this as people call it forward pass, which just means the computer function of the model you want to, evaluate. And computer gradient is called backward pass. That's just a deep learning terminology. So, and if you use deep learning terminology, it means that the forward pass and the backward pass have the similar time. So if you can do the forward pass in O of n time, then you can do the backward pass in O of n time. Because all of these neural networks are some circuits, right? All the matrix multiplication, you can write them as a circuit because they are all elementary operations in matrix multiplication. All of these activation functions are elementary functions. And every component people are using are a combination of elementary functions. So all the neural networks are these kind of differentiable circuits. And if the forward path, the function f, can be computed in some time n, then the backward path can also be done in a similar time. So maybe more precisely, I guess I'll just write down what I'm trying to say here. So in deep learning, so this function f, the function f here corresponds to the loss function, right? On some example, maybe I. The variable x corresponds to theta, because theta is what you really care about as the input to this function. And what is L, which is the number of inputs of the function, that's the number of parameters, because my variable here is really theta. And interestingly, for neural networks, at least from almost all neural networks people are defining these days, maybe there are some small exceptions. In almost all cases, the number of operations you need to evaluate neural networks is proportional to the number of parameters in your network. So, for example, you have a matrix multiplication, right? You have, say, a matrix multiplication with dimension d by d, right? How many parameters you have? You have d squared parameters. And how many operations you need to do the matrix vector product? You also need d squared operations. So in neural networks, it's kind of like the number of operations you need is almost always equal to proportional to the number of parameters. And that means, and then using this theorem, the gradient of f corresponds to the gradient with respect to the loss, the gradient of the loss with respect to the parameters. And it's saying that this one can also be done in time of n, which is the number of parameters. So basically, both the forward path, evaluating the loss, and the gradient can be done in big O of the number of parameters. And that's the fundamental complexity of computing these gradients. Yeah, and in most of the, I think the main job of this lecture is to show you how to do this, how to prove the theorem in some sense. But we are not going to prove it in the most abstract sense because that's kind of too abstract. We're going to prove it in kind of like a language that is similar to the neural networks, so that it's easier to understand. But the abstract theorems holds. And maybe before going into that, let's also see some, in my opinion, some also advanced application of this kind of like idea. So this idea or this theorem is also the basis of some of the second order methods people are using. So what do I mean by that is it means that, you can actually apply these kind of things twice and then compute some of the second order gradient, some form of second order gradient. You cannot compute everything, but you can compute some of them. For example, let's say, suppose, you have this loss function. I guess maybe let's use L of theta as the loss. So this is a loss function. And then maybe I should use J just to be consistent with the notation we have. So let's say we have a loss function J. And, sometimes you say, okay, let me first do one step of gradient descent. I do this. And then I evaluate a loss. So basically, I take some parameter, I take one step of gradient descent, and then evaluate the loss of this. So if you want to compute the gradient of this with respect to theta, suppose you say, I do this d theta, right? I compute so this is itself a function of theta, right? Because theta shows up twice, and you can differentiate it through with respect to theta. And this is still efficiently computable. And why? The reason is that computing this function as a function of theta is efficiently computable because you can compute the theta, you can compute the gradient of theta, you can compute the loss. Each of these three steps are efficiently computable because you just pay 3 times the number of parameters, right? And because this function itself is computable efficiently, then the gradient is also computable. And that's just you use it twice in some sense. And another application is that suppose you define, let me make sure I use the right notation. So let's say suppose you define another one. But by the way, this kind of things is often used in some of this meta-learning situation where I guess it's probably hard to explain exactly, but just in case you are familiar with some of this, like maybe you'll see it later. So you can try to run an algorithm. You can try to kind of like run some training algorithm, and you can, for example, tune your learning rate by backpropagating through the algorithm. So you can tune, for example, you can tune your initialization, and the loss function for the initialization is that if I run this algorithm for 10 steps, what's my results, right? That's your final loss function, which is defined by an algorithm. And you can still optimize that loss function, even the algorithm is involved in defining the loss function. And this is used in some of this test time training stuff. I guess, it's very hard for me to say it, without context, but these kind of ideas is useful for some advanced cases. And another case that is useful is that, for example, you can define G, so you can define Gx to be, say, the gradient of f in a product with some vector v. Let's say you just do this, and then you compute the gradient of G. It turns out that the gradient of G is equals to, this is just a basic kind of like a calculus or kind of like a differentiation. It's equals to the Hessian of f, which is a matrix, times the vector v. So, and you know that this is efficiently computable, right, in all of n time. You know that inner product is efficiently computable. So you know G itself is efficiently computable. And because G is computable efficiently, then the gradient of G is also efficiently computable. And that means that the Hessian vector product is efficiently computable. So this is the Hessian. This is just a vector. So you can compute the product of a Hessian times the vector, any vector, in a very efficient way in all of n time. But you cannot actually compute this matrix itself in the same time, because this matrix itself is too big. It's n by n, right? You have so many dimensions. But this Hessian vector product can be computable efficiently. Okay, so that's all about the abstract stuff, and then now let's try to kind of like see how it works with neural networks. And I'm still staying half abstract, half kind of like concrete. Any questions before I continue? Okay, so the core idea for the backpropagation is that you use this so-called chain rule. So let's review what chain rule is. I think most people know chain rule, but I think it requires some kind of like different interpretations of it, or different presentation of it, so to make it understandable in our context. But maybe question? Yeah.
Some optimizers that use like the second derivative or not. In this case, are we only going to compute like the first derivative?
Sorry. Can you see the sentence? Can you ask the question again? I don't understand the question. You said that there's some algorithm is second order derivative.
Like, is this only for like optimizers like Atom W, or is it?
Atom W doesn't use second order derivatives. I think you need a pretty advanced optimizers to use the second order derivatives. And I think most of the optimizers these days, that are really useful, don't have to actually compute the Hessian vector product. Yeah. So that's what I will tell you about, right? So I didn't tell you how to compute it. I'm just saying it's computable. But how to compute it, that's the whole job of the rest of the lecture. So okay, so let's talk about chain rule, right? So this is how we are going to interpret chain rule in this context, which I think is probably the easiest way to think about it. So let's say you have maybe a this is Z is the input. Let's say you have an m-dimensional vector, which is the input, and you have a function. Let's say U. You can call this function U. Sorry, you have a variable U, which is equals to G, a function G applied on Z. And let's say this is a dimension n. And then later you have another function that applied on U, and make it scalar, let's say R. So basically, if you draw it, you say you have Z, and it goes through some kind of like function G, and then you get this intermediate variable U, and then you go through some function F, and then you get some scalar output J. So what chain rule does, and our interpretation is that, so chain rule basically give you a way such that if you are given the gradient with respect to U, right? The gradient of the final output with respect to the intermediate variable U. So given this, so chain rule will try to compute. Chain rule is this formula that gives you the gradient with respect to Z. So basically, if you know the gradient with respect to the intermediate variable, you somehow know the gradient with respect to Z. So basically, in some sense, it's kind of like, it's how you backprop through this thing, right? So if you imagine there's a chain of kind of these operations, you can compute the gradient with respect to the first variable, and then you can apply this iteratively to get the gradient with respect to the second variable and the gradient with respect to the third variable, right? So if you have a chain of like this. So that's kind of like the main idea. But we are trying to kind of abstract this in a way that you only have two variables, U and Z. U is the output of G and Z is the input of G. And then when you compute the gradient, you start with the gradient with respect to U, with respect to the output of G. And then you can use that to compute the gradient with respect to the input of G, which is Z. Okay, so, and this is actually the exact same chain rule you have learned in calculus, right? So like so basically, if you want to compute the gradient, the partial derivative with respect to one of the variables Z1, Zi, let's say. So how do you do chain rule? You say these are intermediate variables, so I'm going to expand, take a sum over all possible intermediate variables, U1 up to UN. I have n variables here, so I from 1 to n. And I take the partial derivative of my final target with respect to U. Let me say, sorry, let's use J here to not be confused with I. So the partial derivative of J with respect to UI, one of the intermediate variable, and then the partial derivative of J with respect to Zi. Gj is the same as UI, right? Gj is the jth output, which is equals to UI. So that's pretty much how you do it. And if you think about this, right? So these things are these guys, right? And this is these guys. So this equation is saying that dj over dz is a linear combination of dj over du. So basically, the quantities you care about is a linear combination of the quantity you are given. And you can rewrite that as a matrix multiplication. So if you reorganize this, you say dj over dz1 up to dj over dzm. You organize this into a vector. Then this is actual matrix multiplication, where the matrix is the Jacobian, is actually transpose of Jacobian, and this is the input you are given, right? Which is the dj over du's. And this matrix is, I need to make sure I copy paste selection nodes to not mess up the indices. So this is actually the transpose of the Jacobian, and this is what you are given, right? In our formulation, right? So you are given this, and you multiply a matrix, you get the derivative with respect to z, right? So yeah, and you can see that this computation, one magic here is that this computation chain rule only need info about G, the function G, you have to know what the function G is. You have to know the variable Z, what the value Z you are evaluating the gradient at, right? But you don't have to, but not F. But not F. So F is completely out of this picture, right? Even though we have F here, right? Which is, but what F is doesn't really matter. And that's how you make it efficient in some sense. You can forget about what F is. The only thing you have to remember is this thing, dj over du. So even F is a very, very complex function, right? So let's say F is like actually a sequence of like, F1, F2, so on and so forth. It doesn't really matter. As long as I know dj over du, I can forget about how I got all of this what happens here doesn't matter at all. So that's the magic. So in some sense, it's Markovian in some sense, right? You can forget about the past. When you try to compute the gradient with respect to the first variable Z, right? Maybe it's a sequence of operation, right? For example, you have Z, G, F1, say F2, F3, so on and so forth, right? And until you have finally a scalar. And I guess here, the output of, okay, I guess maybe I say, so I'm just redrawing this in a slightly better way. So there's a very complex computation here to get the final scalar. But if you only have to know, once you know this thing, dj over du, you can forget about everything above, and you can get the dj over dz. So this part doesn't have to require the history. So in some sense, you make it Markovian and you can forget about history in some sense. And that's why it's efficient. And I think, in some sense, this mapping from here to here is the so-called backward function. If you look at the PyTorch, like this is for every module, you have to implement a backward function because this module is so this is this function itself is only depends on G and Z, right? So you only have to know the local information to implement the module. And it can compose with anything here. So, and this is the backward function, and the G itself is so-called forward function. So, maybe just to make it more concrete, let's just try to think about this, in some kind of like we have a composition of chain rules, right? So let's suppose you have, so maybe backprop, which is kind of like basically composing the chain rules in the most natural way. Okay, so maybe let's just consider the following situation, right? Where you have, say, the final target is, let's say, a repeated application of many modules, many functions. Let's say you have this. Maybe I should just draw this once so that I don't have to draw it. Let's say you have X, which is mapped to you go through you go through some kind of modules, M1, and then you say you get U1, and then you go through some either modules or functions. I guess sometimes I call it modules because in PyTorch it's called modules, but it's really just a function. And then you get U2, and then maybe you go through another function, M3, and then let's say you get the loss, something like this. So, and so you do this forward computation, and how do you do the backward computation? The first thing you do is that you compute. So step one, you compute dj over du2. And this is, how do you do this? This is just very simple. It's local. You just do some kind of like differentiation, right? You have only one module, so it's easy. And now once you have this, then you use this to compute dj over du1. And how do you do this? This is the backward for this M, right? So use chain rule. Right? This is the same thing as we draw here, right? So you start with, you just assume this part as F, right? So we have the F and G, right? You assume this part is F and this part is G, right? So, and then you apply the chain rule on G, which is M2, right? I think probably I should have a notation here just to formalize this. So you can probably, I think people sometimes, in my lecture notes, I write this. I say dj of this is actual matrix multiplication, and the matrix multiplication is something like is a function of G and Z times dj over du. So you apply this backward function, which is, this is a backward function that depends on the M2 and the variable U1. So these two information to compute the matrix here, which is the transpose Jacobian, and then do this backward pass. And you get this one. And after you get this one, now you want to compute, suppose you want to compute dj over dx, right? So how do you do this? The same way, right? So now you pretend that this whole part is my f. I don't really care about exactly what f is. And this part is my g. And I apply my chain rule. So my chain rule is saying that I can, I get dj over du, which is the same as this, right? That's my input, and I can get the output, which is the dj over dx. So, and here, again, you don't have to know anything about f, you just have to know something about g, and the g here is m1, right? You just have to apply this backward transformation, which is related to m1 and the variable x, and you apply it, this, in some sense, is a matrix, you apply it on this vector, you get on the dj over dx. Does it make sense? And of course, you can do it with many layers, right? Here I'm only showing 3 functions, but you can compose it with any number of functions. You just keep going backward from the beginning. And for example, and another thing is that all of these modules doesn't have to be the same, right? They can be all different, right? Maybe one module here, one of these G is mainstream application, and one of this is the activation functions. Activation functions, for example, you can say, I start with my X. I first do a mainstream application, and I get some U1. And then I do a sigma, the activation functions. I get U2. And then you can do another mainstream application, and you get U3. Maybe you do a layer norm, something like that, You can do arbitrary number of this, and then finally get J. And the same thing, you just have to go backward. But, for each of the individual functions, you have to use the different kind of like a Jacobian in some sense to do the backward. So basically next, we can compute what is the specific backward function, this mapping, for each of the specific operations, right? There's a specific kind of like backward function for the mainstream application. There's a specific one for the activation functions. Each of them has different kind of like Jacobians here, right? So different kind of like a mapping. And we can compute each of them. And once we have all of them, we just compose and get the backward pass. Any questions? So one thing I kind of like I cheat a little bit is that it's not like really cheat, but like what is the variable here we're talking about? It sounds like I'm kind of like trying to tell you that this is the variable I'm trying to differentiate with respect to, right? But if I draw a neural network, do I really care about differentiating with respect to X? I don't really necessarily care about that. Sometimes do, but generally speaking, I care about the differentiation with respect to the parameters. So, but actually that still follows the same thing. The only thing is that you have to think of the variables. Basically, this graph of computation becomes a little more complicated. So what happens is that, so if you have parameters, so then what happens is that you have, maybe let's think about this, right? This has parameters, let's say theta, right? Let's say theta is the collection of the weight matrices and the biases. So, and in some sense, the way you think about it is that you think of this as like you can think of this function has 2 inputs. One is theta and one is x. Okay? So, and now, suppose I already know. So I already told you how to, so like I already told you how we compute dj over du1, right? Because that's just a very simple sequential kind of backward, right? So, and now how do I compute dj over d theta? Maybe let's even call this theta 1 because each of these modules, each of this matrix application has different parameters. How do I compute dj over d theta 1? It's the same thing. It's just like here, you don't view x as variable inputs. You view theta as inputs. So then you compute the relationship. So basically you want to find a way to relate this to dj over d theta 1. But it's the same thing. You just view x as the fixed, and you view this function as a function that maps theta 1 to u1. And then you compute the gradient with respect to theta 1. So basically the input, the data, the raw data versus the parameters, they are just different kind of like matrices in some sense, different kind of like tensors. So in some sense, I think if you write it abstractly, it's really just that this thing is equals to this backward function, which is depends on the matrix application, and you view the theta 1 as the inputs, and then you apply this to u1. So that's how you compute the derivative with respect to the parameters. So actually the real backpropagation actually has this two phase. So and these two phases can interleave with each other. Maybe let me just try to let me see whether I can what's the best way for me to draw this? I think let me erase here just it's a bit challenging for me because on my nose it's vertical and here I need to turn it into horizontal. So, okay, so let's say more precisely, I think with a lot of like notations, I think what happens is that you have X, you have some matrix application, and there's parameter theta 1, let's say, and you map this to maybe U1, and you use maybe a sigma, and then you get to U2, and then use another matrix application, say theta 2, and then get to U3, and then you probably get another sigma, so on and so forth. And eventually you get maybe J. Maybe let's write the last one as matrix application. So let's say you get UK, you get J. Something like this. And you start with, dj over duk. So you, by the way, all of these U's are the intermediate variables, the activations, the so-called activations, right? They are not parameters. And the parameters are folded in the matrix application. So the first pass you do, the first phase or pass you do is that the backward pass is that you try to compute the derivatives with respect to the intermediate variables, with respect to the UIs, with respect to the activations. So you start with this and then you do a backward to get UK minus 1, and then you do this, so on and so forth, and you get U, say 3, and then you compute the backward of this, you get dj over du2, so on and so forth, right? That's the first run. And then once you have this, you can have a branch in some sense that compute the derivative with respect to parameters. For example, from this, you can compute, and with some information about this, you can compute dj over d theta 1. And how do you compute the dj over d theta 2? In some sense, you view theta 2 as so basically you need to go from here to get dj over d theta 2, because you think of this as a function that maps theta 2 to u3, right? Theta 2 to u3 is the analog of the g here, and you already have so basically, in some sense, I guess I'm repeating myself a little bit, but just to make it maximally clear. So you view this part of the things as f in that abstract way, and you say, I'm going to view this as a function theta2 going to u. So you view this part as g, and then that's why how you compute from dj over du to dj over d theta2. And this is really like some kind of backward function of this machine application at theta2 and multiplied with the dj3, something like this. So, and you can do the same thing here, maybe here you can do dj over d theta, I guess, k minus 2, this will give you dj over d theta k minus 1. And you can see that this gradient with respect to the, so to compute the gradient with respect to the first ways, you have to go through this chain and then get here, right? Because this row is what we really care about, the derivative with respect to the parameters. So to get the last one, you have to go compute all the derivatives with respect to activations. But for the first gradient of the gradient with respect to the first parameters, you don't have to go through this whole chain of calculation. Once you get this, you can get here, right? So that's why you can, in some sense, parallelize this, right? So like this is inherently sequential, but some of this can be done on the side, in some sense in a parallel fashion. Yeah. And another thing is that, for example, if you have computed all of this, then you can drop all of the calculation you have done here so that you can clear up your memory. And then this is a way to free your memories, so on and so forth. So basically how you compute this, affects the system perspective a lot, because which tensor depends on which variable or which quantity depends on which quantity, right? And the dependency between them is very subtle. Once you understand the dependency, you can optimize how you compute them in what order, and when you free the memory, when you communicate with other GPUs, so on and so forth. So basically, eventually, all of those depends on this computational graph. Any questions? Okay, so now let's be even more concrete and compute what's the backward function for some specific g, right? So here everything is abstract. We have g, right? So and we have this abstract notation for this backward function, which is this transpose of the Jacobian. But now let's compute for the most concrete things, like for machine application, what's the backward function for g? So let's go back to this kind of like notation. So let's say, suppose you have G, which is machine application. So what does that mean? I think let's assume, say, G is equals to W times Z plus a bias. So, let's say, Z is of dimension, I guess I'm using this consistent notation, is dimension M, W is of dimension, say, N by M, and B is of dimension N. And here, one thing is that we have to think about, and when we have some function f, right? F, your final loss function J is, some f of, I guess, probably I should, let me use U here. So G, this function is machine application, but the variable I called U. So eventually I have a function f applied on U, which is J. So, and, as I said, you can view this as the input, or you can view this as the input. So let's view the Z as the input and compute. So let's say our goal is to say, given dj over du, we want to compute what is dj over dz. So that's, the first task we are trying to do here. So, and how do we do that? We just plug in the abstract definition, right, with the computation we had about from the chain rule. So we know that dj over dz is this matrix times dj over du. And this matrix is that is this guy, right? So it's this matrix. So let's just plug in the values there. So here is the first output, wz plus b, the first dimension, differentiated with respect to first variable, right? And here this is the first output differentiated with respect to the last input, so on and so forth, something like this. So basically this matrix is of the form, each entry is dw plus b, the jth coordinate, which is the jth output, differentiated with respect to the ith input. So this is the one of the entries here, right? And let's compute this thing, right? So it's dzi. Let's expand wz plus b. The jth entry of wz plus b is the, let's write the bj first. And then what is the jth entry of wz? It's just definition of matrification. You enumerate over the inner dimension, which is 1 to m, and have wj, k, zk. So this is the jth coordinate of wz. And now you want to differentiate this formula with respect to zi. And you see that many of these variables has nothing to do with zi, right? So zk has no derivative with respect to zi if k is not equal to I. So it's 0 if k is not equal to I. So you can drop all of those terms. And the only thing that is left is just, and bj has nothing to do with zi, so that doesn't have derivatives as well. So the only thing that is left is the term when k is equal to I. And this is a linear function of zi, so the derivative is just the constant in front of the linear terms, which is just wji. So basically this matrix, the ijth entry is just equal to wji. So that means that you can simplify this dramatically. Right, so if G is the matrification, then actually what happens is just that dj over dz is just equals w transpose times dj over du. So the backward function is just only a transpose. You just transpose your forward matrix and you multiply that, and that's it. So, and you can similarly compute the relationship between this and W and B. So the next thing we want to compute is that what's the relationship between this, like how does this relate to this? Right, if you have dj over du, then what's the derivative with respect to w? And w is your parameter. That's why you care about. That's what we care. For example, here, right? So w is your parameter. So when you have this, then you need to compute the derivative with respect to the parameter. That's why you need to compute this. So that's the next question. And this is a little bit more subtle because it's kind of like it's just a notation is a little bit complicated. So again, what we care about is that we want to know what is, let's just compute each of the wij, right? So, and let's apply the chain rule. So when you apply the chain rule, you enumerate over all the possible ui's, right? So you say, it's take k from 1 to, is this m or n? Let me see, sorry. I think this is n, and you do dj over du, okay, times uk is really just the wz plus b, the kth coordinate, and that is differentiated with respect to wij. So this is the chain rule. Now I'm not using the matrix multiplication because it's a little bit tricky, because this thing is kind of like to write it, because you have so many ij's, like the number of like variables you are differentiating with respect to is kind of like a matrix. It's a two-dimensional. So you need more kind of like tensor notations to write it in a more compact way. So that's why I'm just doing the more brute force way. And but the same thing, you just expand this thing. And let's look at what this means, right? So this is the case coordinate is equals to you first look at the case coordinate of wz, which is wks, zs, and then the case coordinate of b, which is bk. And you are differentiating this quantity with respect to wij. And the only terms that is not zero is the case when k and s is equals to I and j. All the other things has nothing to do with I and j, right? It's all like the derivative is always zero. So that's why the only thing that is left is the I and j term. And for the I and j term, when k is, so basically, okay, let me write down one more step. wij, when k is I, s is j, right? zj. I guess. So when k is not equal to I, this is just zero. And that means that this sum is going to be gone. So basically this is just when k is equal to I, ui times this derivative, the linear coefficient is a linear term. The gradient is the linear coefficient, and the coefficient is zi. So it's just zi, zj. So maybe just rewrite this is equals to. So this is very, very simple. Actually, this is called Hebbian rule in biology. So the way I remember it was, when I was a PhD, was that you have, this Z1 up to M, and you have this matrix multiplication, right? And you get U1 up to UN, and then you go through some network, you get J, right? So that's the picture. And this G part is it's kind of a matrix multiplication. And sometimes people draw this matrix multiplication by the dependency graph. So it's something like this. And you have one edge, which is like maybe one edge we say like this, right? So this is UI, this is ZJ. Yeah. And this edge is WIJ. Right. So, and this edge, the weight is WIJ on it. And the claim is that if you care about the gradient of this WIJ, what it is equal to? It is equal to the gradient with respect to the UI, the output it connects to, right here, times the raw input, ZJ, on the other end of the edge. So I think in biology they say this is a Hebbian rule because the update to the synapses, this is the synapses, is the gradient, or sometimes they call even they call the gradient as the error. So they say the error or the gradient of the one endpoint, the output side of the endpoint, the gradient of the UI, times the value of the other endpoint. So, in functions, it's just equal to this. So this is very simple to compute. And if you use the more kind of like a matrix notation, it's kind of like, if you look at this is a matrix, it's really just equals to something like this, times Z transpose. if you you compact everything into one matrix notation. And what is interesting that this is rank 1. So the gradient for one example and for one weight matrix is always rank 1. And that's kind of like also another useful fact, which is kind of like used in some of the efficiency updates, when people try to improve things efficiently. They use this fact that the gradient is always a rank 1 matrix, but only for one example. In reality, when you have multiple examples, it's not rank 1 anymore, right? So, because you have to average over many examples. But for one example, one weight matrix is rank 1. What time is it? Any questions? And another thing that is much easier is how do you take the backpropagation for those activations. So those activations, fundamentally, you just use the same thing. We can just compute them more easily. So how do you compute the backward for the activations? I guess you have seen the general way. So if you can write it as a matrix application, you should just write, let's say, suppose now let's have another case where U is equal to sigma Z. Right, the function G becomes a sigma, which is the activation function. And then we know that dj over d z is equals to this thing above. So basically this matrix is dji over d z. I guess maybe I don't have to. Let me just write out everything. Times this and this matrix is much easier because this is element-wise application. So the ith output doesn't really depend on the j's input if I is not equal to j. So everything here is 0, everything here is 0 except the diagonal because there's no kind of dependencies between cross queries. So the only thing that matters is this thing and the first output with the first input, that's just the sigma prime z1, right? And up to sigma prime z. I'm not sure what notation I have zm. And everything else is 0, and then you just do this. So this is a diagonal matrix multiplication. You just multiply on the diagonal the derivative. This is all of this sigma here is a one-dimensional function. You just take the derivative of the one-dimensional function and put it on the diagonal. And you can also write this as, I think sometimes people write this as sigma prime z, which is this vector that collects everything on the diagonal, and then you take the entry-wise product of this with this. So this notation often means that you have two vectors, you take the entry-wise product and you still get a vector out of it. It's not inner product. Inner product means that you first take the entry-wise product and you sum everything. But here you don't sum everything, you just list everything as a vector. And you can check these two things is the same thing. Matrix multiplication with a vector, if it's diagonal, you can rewrite it this way. So in some sense, you don't have to express you don't have to write down this matrix even. You just have to write down this vector. Yeah. And maybe another thing is that, it's good to probably recheck whether everything is efficient enough as we claimed, right? So the forward pass is the same as the backward pass. So let's see. So when you have matrix multiplication, the forward pass computing the function takes, if this matrix is m by n, it takes m n time, more or less. And let's check whether the backward thing always takes m n time. I think that's true because here, when you do the backward, you are multiplying the transpose of the matrix, which is the same time as multiplying the original matrix, right? It's also m n time. And here, when we compute the gradient with respect to parameters, you are taking your output is an Iman matrix because you have Iman entries here to output. You have derivatives with respect to each of the coordinates, and the computation here is outer product, right? So it's kind of something like a vector here times a vector here, and computing two outer product takes Iman time. You just have to populate the whole matrix, by the product. So again, Iman time. So the same as the forward, and here the forward is faster because you apply element-wise applications of this activation function. So the forward pass just takes all of M time if this is M-dimensional vector. And the backward pass is the same all of M time because you just have to compute each of the derivatives, the one-dimensional derivatives, and then you take the entry-wise product. It's all for M time. So, so let's see, anything else? No, I think that's everything I have for today. Any questions?
What is sigma?
Sigma, the activation function. I think these days people use I don't remember all of the details of the names. Like there's Jalu, there's a Swilu, there's a bunch of things. So but just some one-dimensional function which can be differentiated fast. And also these days people use this kind of gating. Sometimes you take two matrix application and you take the inner product of them, the entry-wise product of them. And that's another way to do the activation functions. I think actually I added some notes in the lecture notes where you have the references and some of the details. But I couldn't remember all of them off the top of my head, like which one is which. Any other questions? Sounds good. Thanks.